Hi guys, in this video we'll study pericyclic reactions. We shall see introduction and then molecular orbital theory of some organic molecules, and finally we'll see a previously appeared questions in CSIR net. First thing, what are pericyclic reactions? The reactions which proceeds to the cyclic transition state are called as pericyclic reactions. This means that there is no intermediate in this reaction. Intermediate like carbocation, carbanion, carbene, nitrogen, benzene, these things are absent. This proceeds to the cyclic transition state. Next thing is, these are concerted reaction. Concerted reaction means these are single step reaction. Single step reactions. These are also called as stereospecific reactions. These are stereospecific reactions. Pericyclic reactions are stereospecific reaction. What is the meaning of stereospecific reaction? Stereospecific means the reactions in which whatever the stereochemistry in the reactants, that will reproduce faithfully in the products. Look at here, two reactants are there. One is butadiene and the other one is dienophile ethene molecule, trans ethene molecule. In this molecule, the stereochemistry here is trans. Whatever the stereochemistry in the reactant, that will be reproduced in the product faithfully. Such a reactions are called as stereospecific reactions. I repeat, whatever the stereochemistry in the reactant, that will be reproduced in the products. If that is happening, such a reactions are called as stereospecific reactions. Pericyclic reactions are stereospecific reactions. Next we shall see is types of pericyclic reactions. First one is electrocyclic reactions. Second one, cycloaddition reaction. Third type is sigmatropic reaction. Fourth type is chelotropic reaction. Fifth type is 1,3 dipolar cycloaddition reactions. These are the important type of pericyclic reactions. We shall see these things in detail in my coming videos. Before studying these things, we should know some basics like molecular orbital diagram. These are very essential to understand pericyclic reaction. First, we'll understand by taking an example of ethene molecule. Ethene molecule, you know that the molecule formula is CH2 double bond CH2. There is 1 pi bond here. 1 pi bond means you know that it is 2 pi molecular orbitals will be there. Among these 2 pi molecular orbital, one will be bonding molecular orbital and another one is anti-bonding molecular orbital. You may also know that 1 pi bond means 2 pi electrons. When we put this entire information, information diagrammatically, we'll get this. Look at here, there are 2 pi molecular orbital, this one and this one. This one is bonding molecular orbital and this one is anti-bonding molecular orbital. Anti-bonding molecular orbital. So there are 2 molecular orbitals. This one is bonding molecular orbital and this one is anti-bonding molecular orbital. Why this is bonding means here there is a perfect or symmetric overlap between the two loops. Because of that, it is a bonding. and here there is no node. When n equal to 0, there is no node here. Here it is not a symmetric overlap. Here it is symmetric overlap. Here it is asymmetric overlap, and because of that, there is one node here. Remember, ethene molecule will have one node. This is symmetric overlap, and here it is asymmetric overlap. And I told ethene molecule will have 2 pi electrons. In the ground state, in thermal condition, the 2 pi electrons will be over here. So this is the highest occupied molecular orbital. H means highest, O means occupied, M means molecular, O means orbital, highest occupied molecular orbital. And this one is LUMO, lowest unoccupied molecular orbital. In photochemical condition, what will happen? One of the electrons will be remain here, and another will be excited to first transition state. So this is about molecular orbital diagram of ethene molecule. Next we shall see molecular orbital diagram of 1,3-dibutadiene. 1,3-dibutadiene, the molecular formula is CH2, CH, CH, double bond, CH2. There are 2 pi bonds here. This means that there are 4 pi molecular orbitals. In these 4 pi molecular orbitals, 2 will be bonding molecular orbitals, 2 will be anti-bonding molecular orbital. You also know that in 2 pi bonds, there will be 4 pi electrons will be there. When we put this entire information again in the form of diagram, we will get this thing. This below 2 are this one and this one. These are bonding molecular orbitals, and these are anti-bonding molecular orbital. Here there is a symmetrical. Here there is a complete symmetric overlap, and because of that, there is no node here. And here there is one node. Here there is one node. Look at here. This and this, there is a symmetric overlap. This and this, there is a symmetrical overlap. But here, there is no symmetry. So because of that, one node is there. Here it is 2 nodes. No symmetric overlap here. Because of that, one node is there. Here there is a symmetric overlap. Here there is no symmetric overlap. So because of that thing, we got 2 node here. Here there is no symmetric overlap. Here also there is no symmetric overlap. Here also there is no symmetric overlap. Because of that thing, here there are 3 nodes. And I also told that there are 4 pi electrons here. In the ground state, the 4 pi electron can be placed like this, and this level is called as HOMO. HOMO means highest occupied molecular orbital, and this will be a LUMO, lowest unoccupied molecular orbital. In photochemical condition, these electrons will be remain here, but one electron from this will be transferred to excited state. This is the molecular orbital diagram of 1,3-butadiene. Next we shall see molecular orbital diagram of 1,3,5-hexatriene. Here there are 3 pi bonds. 3 pi bonds means 6 molecular orbital. 6 molecular orbital means 3 bonding molecular orbital and 3 anti-bonding molecular orbital. You also know that 3 pi bond means 6 pi electrons. When we put this entire information in the form of diagram, we get this molecular orbital diagram. Here the first 3 are bonding and the next 3 are anti-bonding. When n equal to 0, there is a perfect symmetric overlap. So because of that, there is no node here. When n equal to 1, there is one node. These 3 are symmetrical overlap. These 3 are symmetrically overlap. So there is only one node here. When n equal to 2, there are 2 nodes. symmetric overlap here. Here there is a symmetric overlap. Here there is no symmetry. So when n equal to 2, it is 2. When n equal to 3, 3 nodes. When n equal to 4, 4 nodes. When n equal to 5, it is 5 nodes. And I also told that there are 6 pi electron here. In thermal conditions, 6 pi electrons will be written like this. So this will be HOMO and this will be LOMO. And you also know that in photochemical condition, this will be remain as it is, but one of the electron from the HOMO will be shifted to a higher energy level. This is a molecular energy diagram, molecular orbital diagram of 135 hexatriene. And next thing is, we'll see some previously appeared CSIR net questions. This one appeared in December 2013 and this one is appeared in December 2017. First one is, he asked number of nodes present in HOMO, highest occupied molecular orbital of 135 hexatriene. We studied few seconds ago about a molecular orbital diagram of 135 hexatriene. He asked a number of nodes in HOMO of 135 hexatriene. We shall see just that one only. This is the HOMO of 135 hexatriene. The number of nodes here is 2. So the answer for this is 2. And next question is, according to FMO, HOMO of hexatriene is, which one is HOMO here? Which one is HOMO here? That is a question. So you studied already, you know, there are 2 nodes, right? 2 nodes means, look at here. This is the one node and this is the second node. So this is the HOMO of hexatriene. Thank you for watching.